Today we're going to learn about chemical bonding. We're going to start with just talking about ionic bonds. These are formed when an electron is transferred from a metal to a nonmetal. Electrons are not shared in ionic bonds. Then we have covalent bonds, and we've been learning about these throughout the year. Covalent bond forms when electrons are shared between two atoms. You must know these things. There is another kind of bond. It's a metallic bond. You'll learn about those later on. Now, to determine if a bond is ionic or covalent, we actually have a better way to determine it. It's something called electronegativity. So in the past, we learned ionic bonds are between metals and nonmetals, and covalent bonds are just between nonmetals. Now we're going to learn a better definition. All right, so if two atoms have slightly different electronegativities, the shared electrons are closer to one atom than the other. This creates a slightly polar bond, or what is called a bond dipole. An example is HF. So we look at H. So H has an electronegativity of 2.2. That's what happened there. And F, let's look at F. F has an electronegativity of 3.98. This means that F, with a larger electronegativity, 3.98 is larger than 2.2, can attract the electrons in the bond much better than the hydrogen can. Therefore, F is slightly negative because it is attracting those negative electrons. So this F is going to have a slight negative charge, denoted as delta minus. And hydrogen's electrons, they're closer to fluorine than they are to hydrogen, so hydrogen ends up being slightly positive. We note that as delta plus. I want to mention something here. You should note the general trends for electronegativity. You've already learned trends in atomic radius and ionization energy, and this is not in the notes. You should write this down. Notice as you go to the right in the periodic table, electronegativity increases. That's because you're gaining more protons, so your effective nuclear charge is increasing, and therefore you attract the electrons better. When you go up the periodic table, electronegativity also increases because you are having fewer shells, so the attraction between the nucleus and the outer electron gets stronger because you have a smaller radius. And again, electronegativity is how well you attract electrons in a covalent bond. The farther you are to the right, the more protons you have, the better you attract the electrons, the higher the electronegativity. And the farther up in the periodic table, the smaller the atom, the higher the electronegativity because there's a stronger force between the nucleus and the outer electrons. Okay. So now I said I would explain a better definition for ionic and covalent bonds. And even this definition is not always true. But if you have an electronegativity difference between 0 and 0.4, we say the bond is nonpolar and it's covalent. If the difference is between 0.5 and 1.9, we say the bond is polar covalent. And if the difference is greater than 2, the bond is ionic. Now you might ask, what about between 1.9 and 2, or between 0.4 and 0.5? We really have to look at the character of the molecule itself, or the substance, or the ionic compound, and it's the characteristics of the compound that would actually tell us if the substance is polar, covalent, nonpolar covalent, or ionic. I will not give you test questions that fall outside of the typical ranges and where you have strange properties. Okay, so for some practice, you have this all written down. So what you do is you just check the electronegativities. We're going to look up Al and Cl. We ignore these subscripts. They don't mean anything. We're just comparing the two elements. So ignore the subscripts. Write that down. Ignore the subscripts. Write it down. Okay, aluminum and chlorine. So aluminum, let's see, 1.61. Chlorine, 3.16. Who's bigger? The chlorine. So we will have a bond dipole because the difference here is bigger than 0.5 and it is smaller than 1.9. Let's look at that. Why does that keep doing that? The difference is 1.55, and chlorine has a larger electronegativity. It was much farther to the right, even though it was a little lower. Was it a little lower? Aluminum, nope, they're in the same row. Chlorine is farther to the right. So we're going to point toward the chlorine because the chlorine will attract the electrons better because it has a larger electronegativity. So chlorine has the delta minus, aluminum has the delta plus. HBr, we look up the numbers in the table, you have those. Bromine has a larger electronegativity. The difference here is 0.76, so this is polar covalent. And we point toward the bromine because the bromine has a higher electronegativity. Bromine is much farther to the right. Even though hydrogen is higher up, and we said when you go up, electronegativity increases, bromine is so far to the right that its electronegativity is larger than hydrogen's. So if you have these elements over here, they will always be pointed to. So typically these elements in this range, you'll point toward them for your bond dipoles. Okay, SBr2. What do we do with this 2? Do I multiply bromine's value by 2? No! I ignore the subscripts. Always ignore the subscripts. So the difference here, 2.01. Oh, this is ionic. All right. Not polar covalent, not covalent, just plain old ionic. So we don't draw that bond dipole. CH4, we look up carbon, 2.55, hydrogen 2.0. You find that in this table right here. So hydrogen, carbon. The difference is less than 0.4. So we would say that this is a non-polar covalent bond, and we don't draw in the bond dipole because we say this is non-polar. All right, Lewis structures, how we form these molecules. There's a bunch of stuff written here. You're gonna take that and we will go with it. I'm not gonna read it all out again. So SO2, step 1 says arrange the atoms so the first element is in the center, add the correct number of valence electrons around each atom. So each of those has 6 valence electrons, and you would fill them in 1, 2, 3, 4, 5, 6. Doesn't matter what order you fill these in as long as you put 1 electron on each side and then start pairing them up. I'm going to move these closer together so you can see this. These 2 electrons right here would be called a bond. You're showing that there's a bond forming here, there's a bond forming here. Now, step 2, move electrons so that they are all paired. Notice this is an unpaired electron, this is an unpaired electron. So what you do is you move an unpaired electron to where there is another unpaired electron. And this time we're just going to move this, we're going to move this one over to the left. And that will look like this. All I did was move this electron over to here. Notice in this example, you don't have to draw these lines. You'll see later what this will look like. I just drew the bonds here drew the lines in here showing that these ultimately represent bonds. But you don't have to draw those lines. Okay. So step 3 was check for the octets. These elements are in the column of oxygen, sulfur, oxygen. They're both in oxygen's column, so they both get octets. So we got to check the octets. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. The bonds count as counting as part of the octet for each atom that the bond is between. So this oxygen is okay. Let's check sulfur. 1, 2, 3, 4, 5, 6, 7, 8. Sulfur looks okay. It's got 8 electrons around it. And this oxygen, 1, 2, 3, 4, 5, 6. Oh, this only has 6. We have an 8, an 8, and a 6. We need to fix that. We fix that. You're told right here, we take a pair of electrons, which is called a lone pair, and we move it between the atoms that have 8 and 6 electrons. So I'm going to take a pair from here and put them down here as if it's a bond now. And that will work. So all I did was I took these 2, you take a lone pair. Lone pairs are electrons that aren't part of bonds. I take that pair and I move it down. So now, let's count. Sulfur, 1, 2, 3, 4, 5, 6. 2, 4, 6, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Sulfur's got 8 around it. Remember the bonds, you count them as for both atoms. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Everybody's got an octet, everybody's happy. And now I'm just going to show you what this looks like with the stick structure. For every place where you see 2 electrons between 2 atoms, you just draw in a line, and that line represents a bond. So here we have 2 bonds because there are 4 electrons between these 2. And over here this is just 1 bond because there's only 2 electrons between the 2. This is commonly how you see the structures drawn. All right, CH4. First we arrange the atoms. Carbon in the center. Carbon has 4 valence electrons, so here's carbon's 4 valence electrons. Hydrogen has 1 valence electron, so I put the 1 electron touching each hydrogen. And step 2 is you look for singleton electrons. There are no single electrons anywhere. They're all paired up. Then you check your octets. Let's see. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Carbon's got its octet. Hydrogen. If we look back up at step 3, the hydrogen column does not get an octet. So it's not one of these columns. So these are the only columns that get octets, or sometimes expanded. We'll learn that in a moment. So the hydrogen, we don't do anything because it doesn't need an octet. So we'll draw the hydrogen structure, the CH4 structure with our bonds in place of the electrons. This is one correct way to draw this. This is another correct way. This is the common way that you'll see this in books. All right, next example, SF4. S has 6 valence electron, F has 7 valence electrons, so we draw the structure. I put S in the center. Here's S's 6 valence electrons, and fluorines, each of them is showing 7 valence electrons around them. I didn't do anything fancy. I just put the 4 fluorines around the 1 sulfur, and the dots directly surrounding an atom are its own valence electrons right now. So step 2, we get rid of any singletons. We don't seem to have any singletons, but notice there's a threesome here and a threesome over here. Those don't work. So of these 3, I have to get rid of one of them, and of these 3, I have to get rid of one of them from this area. I don't just get rid of them. They don't appear or disappear. So I'm going to take one of each of these, one from here, one from here, and I'm going to put them over in the corner, still attached to the S. I'm not going to put them around the fluorines. I'm going to keep them with the S's, and I'm just going to put them on the corner. All right. So that will look like this. I took those extra, remember there was a triplet here and a triplet over here. Here's those 2 extra electrons. And I put them, when I have triplets like that, if I have extras, I put them on the corners of the central atom. So now let's check our octets. These are not part of a bond. They are a lone pair on the sulfur. Okay, so fluorine, 1, 2, 3, 4, 5, 6, 7, 8. Fluorine's got its octet. Fluorine, 2, 4, 6, 8. We're good there. And this fluorine, 1, 2, 3, 4, 5, 6, 7, 8. Fluorine's got its 8. Now sulfur, 1, 2. Remember the bonds count as if they're on both atoms. So 2, 4, 6, 8, and 10. Sulfur has 10. Everything else has 8. That is okay. Right here you're told that elements from the 3rd period and below can have more than an octet of electrons, and only the central atom can end up with an expanded octet. We don't put, expanded just means more than 8. We don't put expanded octets on the atoms outside of the central atom. So sulfur here had 10 electrons around it. And that is okay because sulfur is in the 3rd period, and elements in the 3rd period and below are allowed to have more than 8 electrons around them. But everybody else that is in the carbon, nitrogen, oxygen, fluorine, or noble gas column has to have 8 electrons around it. Okay, now here's what this would look like with, what is going, oops. Okay, this is what this would look like with the bonds shown as lines instead of electrons. So here are the lines showing the bonds. And you can see sulfur has 4 single bonds and then the 1 lone pair on the sulfur off to the corner. All right, SO3. Each of these has 6 valence electrons. I'll put sulfur in the center. And this looks really strange, but you can see here are oxygen's 6 valence electrons. Here are sulfur's 6 valence electrons. Here are oxygen's 6, and here's the other oxygen 6. The sulfur, I just had to make sure that I had put at least 1 electron where the sulfur is going to bond with one of the atoms connected to sulfur. And then I had, let's see, 1, 2, 3 are for the bonds, and then there were 2, 4, 5, 6. 1, 2, 3. So, sorry. 1, 2, 3, and then there's 3 more electrons that we're going to have to do something with those. So first step is make all the electrons. We have to pair them all up. So we're going to move one of these electrons, move this electron over to here. You could do it either way. There's no one right way to do these. So I'll move this one over to here. And now I still have a lone one over here. So I'm going to take one of these 3 and put that down here so that that would now be paired up. This first part, pairing up all of the unpaired electrons, there's no real clear way to do it. You just have to make sure that no electrons are sitting by themselves. So again, I'll just take this one, put it over here, and with this little threesome over here, I'll take one of those to even this one up. And I get something that looks like this. So now it's time to check the octets. Let's see, this O, 2, 4, 5, 6, this does not have an octet. Sulfur, 1, 2, 3, 4, 5, 6, 7, 8. Sulfur's okay. This oxygen has 8 around it. This oxygen has 8 around it. So everybody's okay except this oxygen. Remember before, when we had a 6 and an 8, we can take a pair of electrons and move it between the atoms that have 6 and 8 electrons. So I took this lone pair up here, and it doesn't matter which oxygen oh no, it does matter. You want to put this with the oxygen that had only 6 valence electrons around it. Well, they're not valence, but they're the valence electrons from all the atoms. We're going to take these 2 electrons and put them over here so that now the sulfur still has its octet, and then we're giving oxygen 2 more. So now this oxygen has an octet. Sulfur has an octet. Oops. This oxygen has an octet, and this oxygen has an octet. And this is what this would look like with the lines instead of all of the little dots for electrons. Okay, time for CO2. Carbon has 4 valence electrons, oxygen has 6. So now I have to get all of these singletons paired up. So I have a singleton here, a singleton here, a singleton here, a singleton here. You can do this however you want. I just would choose to take this one and put it over on that oxygen, take this one, put it on this oxygen, and that would look like this. Then we check for our octets. This oxygen appears to have an octet. This oxygen appears to have an octet, but the carbon only has 1, 2, 3, 4 electrons around it, and it needs 8. Remember how we get extra electrons when they don't seem to be anywhere? We take a lone pair and we turn it into a bond. So if I did that once, that would give this carbon only 6 total electrons. I could take another pair from this oxygen, put it down here, and now this carbon would have 8 total electrons. There are so many correct different ways to do this. You'll have lots of questions in class, I have no doubt, and we will talk about that. In the end, what's important is that everybody has an octet. I have the right number of electrons in here. This is with the bonds, the lines. And could you have 3 bonds on one side and 1 bond on the other? Yes. And again, I will answer questions, but this is the most correct way to draw this structure. Okay, I think this is the last one. Aluminum chloride. Aluminum has 3 valence electrons. Chlorines have 7. So all I did was take my chlorines with their 7s, put them around the aluminum with the 3, and then I check for the octets. Chlorine has an octet, chlorine has an octet, chlorine has an octet. Aluminum, 2, 4, 6. Makes you think you need an octet, but you don't. This is a little. Aluminum is not in any of these columns, so aluminum does not have to have an octet, so we are fine with aluminum. Just to simplify this, elements that are in the boron column, the beryllium column, the hydrogen column, these 3 columns do not need to get octets. We won't be having any of these elements in molecular compounds, so you don't have to worry about the D block elements. But things in the boron column, the beryllium, and the hydrogen column, these all do not get octets. Everything from the carbon column on gets octets. Everything from this column and below, all of these elements down here can have expanded octets. Period 3 and below, and typically just, in fact, yeah, typically just the elements from the phosphorus column and to the right. But you don't have to worry about that. You'll see it when it happens. So we were okay with the aluminum. And the stick structure way of drawing this, I just replaced those electrons that are being shared with the bond. And everybody's got its octet. Okay, now we've learned Lewis structures. You'll need lots of practice. You'll get lots of practice. Valence shell electron pair repulsion theory. This is to figure out what the geometry is of the molecules. So we have some definitions. The lone pair, we've been talking about those. This is a lone pair right here. This is a lone pair right here. This is a lone pair right here. Those are pairs of electrons that are not part of bonds. Okay, steric number. It's the number of lone pairs and atoms bonded to the central atom. A double bond only counts as 1, not 2, because there's only 1 atom bonded to the central atom. So we count the bonded atoms in lone pairs. So aluminum, 1, 2, 3, steric number 3. Let me find one with a double bond. Okay, carbon, this steric number here would just be 1, 2. We don't count bonds, we count atoms bonded to the central atom. So there's 2 bonded atoms and no lone pairs. We're counting atoms, not bonds. Electron geometry right here, and then molecular geometry. On the molecular geometry, it's like you're not seeing the electrons. Here's a big chart. It shows you everything. Don't panic. We will go over this in class. We're just going to use this chart as a way to figure things out right now. And you'll get a big picture of this in class. You'll get a handout of this. So let's do these problems that we've already looked at. We have SO2. What's the steric number? It's bonded atoms. 2 atoms are bonded, and there's 1 lone pair. So that's steric number 3. Number of lone pairs is 1. So we're going to look this up. Steric number 3, 1 lone pair. Steric number 3, 1 lone pair. Okay, here is my molecular geometry. The electron geometry is the top row. Notice it says electron geometry. This top row is always the electron geometry. So the electrons are trigonal planar. You should write the name and draw in the picture. And the molecular geometry is called bent because we're just looking at the solid lines. It's like you don't see this little lobe up here. Those are the lone pairs of electrons. And the angle would be 118. So there it is. All right, CH4, steric number, 4 atoms bonded, no lone pairs. So this would be steric number 4, no lone pairs. You look this up on your chart. Steric number 4, no lone pairs, tetrahedral, bond angle is 109.5. And the electron and the molecular geometry are the same because there's no lone pairs. That's what this says right here. So you write the name and you draw the little structure. Tetrahedral, tetrahedral, bond angle was shown in the chart. Okay, SF4, there's 4 atoms bonded to sulfur and 1 lone pair, so steric number is 5. 1, 2, 3, 4, 5, and 1 lone pair, 5, 1. You look this up in the chart. Steric number 5, electron geometry is here, right here, trigonal bipyramidal. 1 lone pair, seesaw. So imagine that this lobe isn't here, and all you see is this, what looks like a K there, because this is lone pair. The molecules, what are the atoms doing? You don't see the lone pair. It still has its force, but you don't see it. Okay, and we're not going to talk about bond angles for that. They happen to be 90 and 120, but you don't have to memorize that. All right, SO3. 1, 2, 3 bonded atoms. Doesn't matter how many total bonds there are. It's just 3 bonded atoms, no lone pairs. 3, 0. You look that up in your chart. You should find that that is trigonal planar. Bond angle 120. CO2. 1, 2 bonded atoms, no lone pairs. 2, 0 is linear. You should look that up. And you see that bond angle is 180. Again, in class, I'll give you a way that's really easy for memorizing these. Now the aluminum chloride, 1, 2, 3 bonded atoms, no lone pairs. Trigonal planar, 120, and that is